Bildschirmfreigabe Nummer 3. Let's open the chat and where's the attendance list here? Okay, so last time we took a look on flow control structures and and pointers, of course, and since we want to proceed somewhat pedagogically correct, the next logical thing to take a look on will be structures. So let's create a new project. Console application. Okay, and as soon as it's created, we can clean it up a bit. So in C, you have such a thing called a structure. You start with a struct, then you can give it a name like my struct. Then you open and close curly brackets, and within it you can specify members of the struct. So for example, int variable a, and int 64 variable b, and maybe a char and a short, another char, char, yeah, var I. Why is it complaining? Because I missed that here. So the idea is that with structs you can bunch together a couple variables, and then you can refer to the variables through the struct. So let's first define a variable of the type struct. My var, or my struct. Let's call it my struct. And now if you want to access one of the member variables, you can just press dot, and then you can access those members. And the main advantage of a struct is that this is a consecutive memory region. So if you would just have variables without a struct somewhere in your program, in your function, then where they would live in memory and whether how they would be aligned to each other would be up to the compiler to decide. So of course, in a simple case, they would be just in the same order as you provided them, but if the compiler does optimizations, it might remove some of the variables, move them around, etc. We use the same memory area. There are a lot of things that compilers do to optimize the code completely automatically. If you, however, create a structure, then you define exactly how you want the memory here to look. So let's first maybe initialize with some values. You can initialize it in a similar way as you can initialize an array by providing curly brackets and then typing values in the order as they are here provided. And what you also can do is you can get the size of the whole memory block. Const int, let's call it my size of. Then we can get the type, or you can of course in size of also use the variable name itself. But let's go with this, and we see here that it tells us that the size of the whole thing is 24 bytes. So let's calculate whether that makes sense, or maybe not. So, yes? In C++, technically, classes and structures are almost the very same thing. In just C, in plain C, you have only structures, you don't have classes, because plain C is not object-oriented. C++ is. The only difference in C++, so when functionally, if you have a file that has an extension CPP, then the Visual Studio will compile it as C++, and if the extension is just C, then it will compile it as just a C file. You in fact could actually change this when you click on that properties, then you can select, can you? Maybe you even cannot. It will always go by the extension. Yeah, it always goes by the extension, so you cannot even change this. If you are compiling like by command line, then there might be a way, but not through the UI. So if you have a C file, then you cannot use classes within it. The other way around works just fine. And to them, pretty much only difference between structs and classes in C++ in the default scope of members for a class is private, so you need to explicitly specify that you want them to be accessible publicly or in a protected way, while the default access for structs is public. So everything that you put in a struct without specifying its access scope will be public by default. It's a very subtle difference, and functionally the compiler will compile them more or less the same. It just has a different small assumption. Okay, this much to that. Any more questions? Yes? In C++, yes. In just C, kind of. We will take a look into the kind of option today. We will take a look on proper inheritance of C++ once we arrive at the C++ part of the course. Any more questions? No more questions? Okay, then let's continue. So we found out the size of our structure. Now we want to check whether it makes sense. So we have here 4 bytes, here we have 8 bytes, here we have 1, here we have 2, and here we have 1 again. And if we add all of that together, it will not be 24. That much I can tell you already. Yeah, I'm wasting a bit of time in trying to nicely format. Damn it. Like that. So the result is 4 plus 8 is 12, 13, 14, 15. That's like 16 if I didn't miscount. So where are the missing 8 bytes hidden? Well, they are hidden, or rather they are used for memory alignment. So when the CPU accesses memory, it does this in blocks of 64 or 128 bits at a time. So when it loads this data into the cache, if you would use random offsets, especially overlapping to such 64 or 128 bit boundaries, for the CPU it would mean that it might in order to just read this one short here, need 2 memory access operations instead of 1. This is something that is very much an implementation artifact of how the memory controllers and memory nowadays operate, but it has a very significant performance impact. So when defining, and it was like this since a long time, so when defining the language and structures and etc., the idea was that by default the structures will be memory aligned by the compiler. So what it will do here is, at this point it will enter, so it will, since the biggest variable we have here is 64-bit, it will try to memory align everything to 64-bit. So it will add here a dummy, a non-existing variable, a dummy, just unused space of 4 bytes. So here in total we have 8, so this would be loaded in one go. This can be also loaded in one go since it's a 64-bit variable. And then when we continue, this is fine, this is also fine. This is also fine, but to work with sufficiently let's say with sufficiently nice memory alignment, it will automatically add here also some dummy of 4. So in total we will now, if we would calculate everything together, we would get at our 24 bytes that we see here are reserved for the structure. Yes. What else? So this is one thing that really needs to sink in, so to say, because on an intuitive level one would always assume the objects to be just aligned one after the other with no intentional empty spaces, but in fact they are. For example, I mean, we can change it slightly to make it more obvious, like this. This is still the same size. It's still 24 bytes because it keeps the amount of reserved memory the same. Okay, so now which other advantages except for memory alignment does this structures offer us? Well, I'm glad you asked. we can define also pointers to structures. So my struct asterisk, my p pointer to struct is equals reference at my struct. And now you can also refer the member variables, but in a slightly different way instead of using a dot. So maybe first we should simply write down the access examples. So int a is equals my struct a how b c d e b c d e b c d e. Oops. I somehow got my fingers entangled. So we had int 64, we had char, we had short, and we had another char. Okay. Genau. So this match to this, and if you want to do more or less the same thing but with the pointer, there are in fact two ways how this can be achieved. So these are already defined. One option is you just use the arrow operator instead of the dot. This is quite useful since it makes the syntax clearer. And alternatively, you could of course write asterisk bstruct dot. So I can int underscore is equals dot var a. So this works like a bit like this. So this of course is not a nice syntax. It's a bit cumbersome to read and to write, hence the arrow operator. In fact, the arrow operator will be quite useful in later things as well, because it allows us to create smart pointers and custom objects which behave like a pointer but have some internal logic. But this we will take a look once we arrive at the C++ part of the course, as many of the more fancy things. First we need to go through the basics. Okay, and the next thing, so first of all, why is this useful? It is useful because if you are calling functions, which we'll take a look later this lecture, then so I mean today's lecture, not like function calls are not far ahead. We will be there soon. But the thing is, as you know from probably any other programming language, you can pass arguments to functions, obviously, and instead of having to pass like 5 arguments, all of those, you can just pass one pointer to the structure, and then that saves you typing, and then you can refer to the structure within your function. Another interesting and useful thing that structures offer is that they can be, while they are not a machine type, so for the computer it's just a large blob of memory, and how it interacts with it is up to the program, but the compiler abstracts away from us this non-nativeness of the structure, such that we can, for example, use a simple assignment with a structure as we would use with a normal simple operation. So let's call it my struct2. So we create another structure, and now we want to just assign all the values from our previous structure to this one. And when we do this, the compiler will internally generate code which will go through the whole memory range and copy each variable one after the other into the new, or rather into the other memory block. So this also helps us a lot when writing code, that it helps us to reduce the complexity. One interesting thing to keep in mind with regard to classes, since we already talked very slightly about classes just before, is that usually, while they are more or less the same as structures, there are certain conventions of how you ideally should use both. And with structures, you would try to create them such that you really can use this copy operator. So you would not put things into a structure which would lose their meaning once copied onto another memory region. With classes, you don't have these restrictions, so ideally you are trying to pass classes around always using pointers or by reference, which under the hood is the same thing, such that within classes you can have a lot of very convoluted internal states which once copied into another memory region would become meaningless, or rather invalid, plainly invalid. An example of such a member would be, for example, some sort of pointer. So if you would have a large array in the class, a large array in your structure, I can write a short example for that. Testing. So let's say we have here an array, int my array, it has 100 elements, and then we have int asterisk my pointer. So if we now would copy just this structure, then the array gets copied, like really by value. Everything that's in it is duplicated into the other memory region. The pointer's value is duplicated, but if we would at some point in our code's execution have something like this, reference pointer at 10, for example, why is it complaining? We have a reference with an integer. Yes, that's of course a member, so it needs to be shit, I need to comma. So now the pointer has a meaning. It points to the technically 11th element in our array. As you remember, the numbering starts at 0, not at 1. But if we would just copy this memory, then in the new structure, so let's do this just as a small demonstration. myText2 x2 so myText x2 is myText2, then pointer would still be equals this. Well, it's not really valid. So at this point, if we would no longer have access to memory of test X, then the pointer would just point into some invalid memory, which would be a major problem. And this way you should not use structure. So with a structure, you would really want to only put in values which, after being copied, would still be entirely valid. So you would not want to have a pointer that points to itself. You would somehow here after the assignment need some additional code to change the pointer of your copy to point to the right position in the array, in the new array created. And in C++, what we do is we usually, if we want a class to be able to be assigned by using an assignment operator, we overload the assignment operator for the given class and write some own assignment code. So it will not only copy the memory, but also intelligently update all the internal states of the class. But since this needs to be explicitly taken care of by the programmer, if you don't intend the class to functionally work like a simple variable, then you should just not copy it this way, and always refer to it by the pointer. So this helps you to avoid programming mistakes. So let's now take a look how this would look in assembler once it's run. So how much code was actually created for this simple assignment operation. As you might remember from our normal variables, an assignment usually takes 1 to 2 instructions, not more. So let's look here, and as you see, it's actually quite a few more. It's 6 instructions, and here at the end it has this rep moves, which is something that is only available, well, maybe not only, but it's something that is a part of the x86 assembly language, and you don't have a analogon of that available in RISC type architectures. I'm sure there are some exotic architectures that will have something similar. So the idea how this works is, first we load the address of both structures into 2 different registers. We load addresses using the layer opcode. Then here we fill this RDI and RSI variables with these addresses, which we have here, and then to the ECX variable we write 18H, so that will be in decimal. No, x18. Okay, we need to disable hex. 24. So as you see, it's actually the size. And then we start this reps moves operation, and what it will do is the reps opcode will repeat an operation that is specified after it the amount of times as specified in the ECX register. So it is a mechanism within the CPU how you can implement in a way very simple loop. So normally if you would think about how you would copy a large memory block, you would make a loop that starts at 0 and goes up to the size of your memory block, and then you would copy within the loop 1 byte at a time. And then you would need a comparison operator, so the whole code would become even more complicated. Here, through the use of this reps opcode in combination with the move operation, this is really done by the CPU in one line, so to say. And the way it does is it will take the value at the RDI location. So which one is the target? 2 is the target. Yeah, RDI, D is like destination, so it takes the value of at the RSI position and copies 1 byte to the RDI position. This could in fact even be made more effective, since I think you can also specify here double word or Q-word as the granularity of your moves operation. But for this case, the compiler just chose to do it 1 byte at a time. So if we step through the code, we see that each line, well, each operation is executed once, and then if we try continue stepping, you see that we are still at the same position. So, and one more thing, you also see here that the RSI and RDI registers are changing, since the operation here will increment those registers automatically for you. So, doing the same thing in a loop would really take forever. And we see here as the RCX register is getting less and less as we step through the compile, and once we execute it enough times, it finishes. So of course at this point it still needed a lot of CPU cycles, so it wasn't the most efficient thing ever, but it finished. And of course if we would compile in an optimized build, then it should improve the code significantly. I'm just worried that probably if we enable optimization, let's switch to the release build simply, then it will completely remove the variable, since it's not used for anything anymore. I mean, we could maybe return one of the values, but I would assume that it will probably kill that anyways. Yeah, as you see, it pretty much just reduced our code to return 2. So the optimization is it's too good basically for the purpose of simply demonstrating things sometimes. But just for comparison, we can in fact write the operation here as a normal loop. So the same thing would be for int e is equals, we should actually use size t, comma is smaller size of my struct I++, and now so reference struct2 char asterisk at e is equals at e. Okay, so if we run this, as it's still the release, but I should switch back to the non-optimized build. Yes?
Using size t here because the size of my struct could be something unexpected, but large for an integer to handle, for example, or what is the reason?
It is customary to use size t for your loop iterator. Effectively, we will not go with a structure past the 4 GB boundary, so it doesn't make a difference effectively. But if you would write some code that later handles memory addresses, it is better to use size t, because you will have the good habit of always using a loop variable that is large enough to carry any reasonably large value. And performance-wise, while it would in theory use more memory than just an integer, since it fits into one register, it will be just as fast as if you just used an integer. So it has almost no downsides, and the upside of getting the right habit from the get-go. Okay, we see here that it's a bit. And so does this answer your question? Can we continue? Okay. Okay. So as we see here, the generated code is quite significantly more complicated than the before code. So the execution would be slower. So this is one of the obvious advantages of using structs. And now, well, maybe one last thing. If the struct is small enough, so this one is actually quite big, but if we would remove some of the variables, let's remove that. Will always big. We can make a second test case here. If you have an extremely trivial struct, the compiler can, if it's smart enough, if it is, we will see, optimize it even down to a to not need a repeatable instruction. If your whole structure just contains a few characters, for example, C1 and C2, then technically you should be obviously able to copy it just using one machine instruction. Whether the compiler is smart enough to do this, we can see by this simple test. I'm not sure what it does in a what is complaining. I used v1 somewhere. Yeah, this is not initialized. We need to initialize it with some values, otherwise it will complain. Was it smart enough? And yes, as you see here, it was smart enough. So instead of needing even though a hardware says that loop still a loop, here it really just loads the value and then saves the value, and voila, you have copied two variables with the computational overhead of only one. And I think we could go even up to integers with this approach, at least on a 64-bit platform. So let's quickly test this. Zack. As you see here, it's the exact same operation, just that instead of word it used quad, which is 4 times as big. If we would, however, switch this to a 32-bit, then since the whole thing is 64-bit and the compiler doesn't have quads available, it will in fact need to be more complex about the operation. But still, instead of implementing a sort of loop, it just opted for using two copy operations, basically copying the two variables one by one using the double word data size. And of course, as it grows, at some points it just switches to this reps moves sort of behavior. But since many structures can be very small, then this is something that usually really helps in improving your computational performance of your program. Okay, so now, since there were questions about inheritance, we can take a look onto how one would implement a sort of inheritance using C without the ++ part. So let's but well, wait, before that, one more thing. We can rewrite this structure in a more memory saving way. So let's maybe first do this. So let's call it mystruct2. I'll just copy it from here. mystruct2, and our goal is to reduce the memory usage as much as we can. And one approach to do this would be, let's see, we just move the int down, then it should be it. Let's measure its size. Oops, this would be var size. So here, my var size 2, and it is, wait, it's still 24, that should be right. Okay, let's try something. Okay, this one is 12 is still too much. I see the problem. And wanted this to be aligned as well. Now it works. So by a smart alignment of the variables, you can reduce your memory footprint quite significantly. So when you are creating, or well, when you are designing your structure, you should maybe keep this behavior in mind and try to optimize it. So in the before case, when it was like this, unfortunately it did not align properly, as we have seen, apparently because it wanted to align var_d with a byte boundary as well. So yeah, things to keep in mind. Plus we are still in 64 in 86 mode. If you switch to 64-bit, it will more or less should behave the same, since by definition they should the structure should be compatible. So even though it has more abilities to align things better in the 64-bit case, it will do the exact same alignment. This way, if you have a program and save your some 32-bit or 64-bit data-based data structure to a file and then read it in a program with another bitness, usually it should look the same and work the same. Of course, then you would need to take special care how you treat your 64-bit variable. But since modern compilers, even on 32-bit, offer you the in64 keyword and then just implement the operations using multiple 32-bit operations under the hood, it is not really a limitation. Okay, but since we have already nicely memory aligned our structure, now let's try to create something that resembles inheritance. So what you can do here, for example, in normal C, is you can put one structure into another structure. So let's do that. Struct my struct extended. Then we just say that the first variable will be of type struct2. We will call it struct stx, maybe str is usually reserved for string. Then we can add some var f, and voila. And now the way we can of course access it is let's maybe create a structure of this type, my struct x zack. So for the first variables you need to access them through this intermediate member, let's say. Let's see, a e and f is not longer at this level. We have one too much. 2, 3, 4, 5, 6. And in fact what internally is generated from this sort of design is in the memory pretty much identical to just having all the variables at the same level. So if we need a name 2. So let's take those. Zack and this. Zack this, that's right. Exact. These two structures, struct x and struct x2, are functionally identical. So what we, for example, can do is we can create a pointer of this type, my x2, and assign to it our other struct. Of course, it's a different type, so the compiler says, "May you are not allowed to do this," but of course we are smart. We can use typecasting to tell the compiler to do it anyways. And now if we just put a breakpoint here and run it, and then we can inspect the content of my struct2 of my struct x2 in the locals. My struct x2, as you see, it contains the same values as we have assigned to the other structure. So in memory those structures are identical. So what you could do for your inheritance is, if you have some newer application, then one thing of course is you can just add variables and then just don't use them if you don't know that they would be set by your original structure. Or in fact you can just take your old structure and put it in some new structure and then use the whole thing as a new as your derived in quotation marks class. And one other thing which is quite useful, I would say at this point, is maybe to take a look on how Windows does this. So on the Windows API has a lot of different functions which take whole structures as an argument, and the way they allow themselves to extend those structures with newer versions of Windows without breaking compatibility is by adding a size field to the beginning of each structure. So the typical Windows API structure would look something like as my API, let's call it just my API struct, just API struct. They have a size t size field, and then they have the rest. This way, this way, once you initialize the structure, usually would do it somehow like this. As API is equals size of the initialization here. If you only provide one value from some, works the same way as in as with arrays. For the provided places, it fills in the provided value. For the rest, it fills in 0. So we can now run it, and then within a function that will be using this structure, you can just check your size field. So as you see here, everything is 0 except our size field. Now our size, of course, increased since we added here the 8 bytes for the size. And of course, one thing to note at this point is that if we would compile this in 32-bit, then for size t it would pick a different size. So this may or may not, depending on the other classes, change our memory alignment. So in this case, it stayed 32, but if we would have a different memory alignment, it would in fact might invalidate the structure. So if you create a structure and you want it to be portable between different architectures, you should stick to the types which are not platform dependent, obviously. Yes. So then but coming back to our Windows API example, within a function, for example in your library or whatever, where you would then take some structure as an argument, you can check the size field, and then you just know, depending on the size, how many of those variables are still available. So for example, if we would have some older version of our structure, struct old, which doesn't have the f, then structure 2, old, let's go with old for consistency, size of structure also. Of course, we see here that this is now initialized to a smaller value, and now if we run the code, you will actually, we should do something else before we run it. So within your function or your library, you would have two ways how you can handle different sizes. One would be that you just check the size, and then so one would be if we need a pointer. So let's say we have some void pointer arg1, argument 1, which is just, let's say it's the old one. So the one option is, of course, that you just cast your argument 1 onto one of the structures and then check. What you also could do is just you say size the asterisk, I drop the G, arg1, and dereference that. So if this is size of, so it would of course be also a great place to use a switch instead of an if, since the values are fixed and the comparison are simple. And now, depending whether you assign old struct or a new struct, you would end up in one of the two cases, and within those you could then say, okay, we see that the size is this, so new is equals arg1, while in the other case you would go old on, and then you would do something with your structure what you want to do. This is what this, wait, what did I forget here? I forgot the asterisks. You of course want to use the pointers here, and this is one way how you can differentiate. The simplest way, option 2, is to just use your use this one. Just assume that, just always use the new structure, because you know that the new structure contains everything they all did plus a few things. And then further down the line, if size one new size equals new, then size new f is equals 1 to 3, I don't know, something. So just make the size check before you access the other structure. It would be, with this scheme, highly unrecommended to change in newer versions of your structure member variables. What you can do is you can leave them in place and just make them useless. So that's say that with a newer version this parameter is ignored or something like that. You should not try to move them around and then deduce by the size which version it is. What you of course also can do, which is used in some more modern APIs, is that you just create a structure. Let's call it API v2, where instead of a size field you just use a, let's say, an integer version, and then you just pass version 1, version 2, version 3 and so on, and then you only expect the first value in your structure to be the same, and the whole rest can then be arbitrarily different. So in this case you would of course need to use option 1, and arbitrary so this gives you more flexibility, but of course might make your code more complicated, since then you really need to implement the whole function multiple times for different versions of your structure. The way Microsoft did it was to save on memory and to keep the program binaries as small as possible, so it was more easy to just use the same structure, and if they add some variable at some later point, then just at that point explicitly just have a check in the code whether to use it or not. Okay, so this much to structures. Are there any questions about structures at this point, or can we proceed to the next structure like sort of object? Okay, if there are no more questions, or no questions at all, then let's proceed to the next thing, and these are so-called unions. So while a structure, as here depicted, uses separate memory regions for every member it has, unions work differently. They use the same memory. So so if we have here, let's just for the sake of simplicity go with this simple test case, suck, and then int my union size, like size of my union. Does anyone has an idea what the result will be here? Okay, well, if no one, the result is 8, because the largest variable is 8 and all the other variables are mapped onto the same memory area. Unions are, the usefulness of a union might not be directly apparent, but in fact they are quite helpful if you want to implement well, quite a few different things. So we'll now take a look to a few of them. So first of all we can just test how it works in practice. So let's assign to our var a the value x1 2 3 4 5 6 7 8 9 0 a b c d e f. Wait, that is that should be enough. Yeah, we of course need to define our union first. Okay, and now we can just look into the locals view to see how this really looks. So we have our my union here, zack, and we go to the hex view. and as you see, it is the whole memory area, and then it just maps the last, so in this case the last 4 bytes, in this case the last 2 bytes, and in this 2 cases the last 1 byte onto this one member. So one thing we already, for example, exemplary useful use case that we already can see here to do something with our union would be that we can use it to take apart some sort of larger integer or larger object. So let's go with union my quad word. That is maybe one thing I forgot to mention before, this nomenclature with word, byte, and etc. So the size of a word is very much architecture specific, but on x86 historically the nomenclature is that a word is equals a short is equals to 2 bytes, 2 bytes, and a d word is what it says, it's a double word. Like an int. And the q word is a quad word. We drop the R, which are 8 bytes, which is then a int 64. So that's the nomenclature. As far as I remember, on ARM it's kind of the same, but if you go to other architectures, it will not be the same. And with ARM, I guess it's also to a large what's the right word? It largely depends on which version of ARM you are using. So the typical version 8, which is 64-bit, will adhere to this. If you use some 8-bit version as used in microcontrollers, then your word might be just 2 bytes on this simple RISC architectures like used by EVR and others. So yeah, but since we are here on a modern x86 platform, we use our QWORD. And now, so first of course we edit our int64 origin variable QWORD, and then what we might for example want to do is we want to split it into 2 integers containing the first upper and the lower half of our quad word. So this is something that would be very useful if you want to create some structure which you can use on 64 and 32-bit systems. An example of where such a exact structure is used, for example, is for file sizes on Windows. They have a large integer structure which is made up of 2 32-bit variables, and which also on modern platforms can be just referred as one large 64-bit QWORD. So here we have our initial value, and then we can write struct, and within this struct we can then provide int value high and value low. As you see here, we don't provide a name. We can have these anonymous structures within other structures or unions and vice versa, so that now if we assign a value to QWORD, value punct QWORD is equals this. And now inspect this in the in our locals. What is structure value? Then we see that the QWORD contains the whole thing, and the 2 variables value low and value high contain accordingly the high and low portion of the value. Yes. So this is already one example how such a union can be very, very useful, because it allows you to define some value overlap, so to say, which then you can use in your, for example, you could say if value high is the lower part. Actually, I think I switched those. It should be like this. Because value low should be the lower bytes, and value high should be higher bytes. So for example, you could have here if value high is equal to 0, then you do something, and else you do something else. And the interesting part here would be, for example, that you could check that if value high is 0, then you know that the value there can be passed maybe to some 32-bit API and does not need to be copied down into a different memory range or something like that. So this is one useful use case. Okay, now it works. Wait, high are the first ones. Yep. Now the order is correct. And the same thing as we just did for just the quad word, we could also do to dissect a variable even further. So to save on typing, I just prepared here a small example, which we can just paste down here. So here you see that we now it's still the total size of our union will be 8 bytes, but it allows us to access those 8 bytes in any way, shape or form that we might find useful within our program. We can access it as one large value for a mathematical operation. We can access every byte individually. We can access it in increments of short if we would want that, or here we can also access it as we already did here for the high and low value, which also are not quite right. Low, yeah. Suck. Yes. So, and of course, a simple example is value. So we can use as many dot or arrow operators after each other as we want. So you can have like a variable. We could also create a pointer to this. We could have like union2. Have u2 is equals reference on this. Asterisk. So there we just would need to switch to the arrow operator. So this allows us quite flexibly to access all the bytes. And another example, for example, where such structures are used is when using network sockets. IP addresses, like the network socket structures which contain IP addresses and other parameters, often use such unions because you might want to access the representation of an address in different ways, depending on what you are doing. So sometimes you just want to copy the value as quickly as you can, then you can use just the integer value and then copy it in one go, or you want to get every single portion of your IP address, and you would go to byte by byte, etc. And the last thing that you can do with structures and unions, which is quite useful, is you can use it for to define bit fields. So as you might remember in the first lecture where we took a look on variables and the operations you can do with it, one of the examples that I showed you was how to use the different logical operators to access individual flags within a 32-bit variable used as a bit field, which appears to be a bit a cumbersome way. Of course, it saves you a lot of memory, but at what cost? You need to type a couple letters more. So there is in fact a much nicer way how you can access different values in a flag field. So let's do that. Define as a union, my flag union. Suck. Then we of course define our I have a typo. I don't think so. So this will hold our whole values, and then we just make a struct like before with the high and low part, just that here we can now really specify whatever we want, and we in fact can access individual bits of this thing. So we go again on C unsigned int, then byte 1 doppelpunkt and the count of bits we want to use from our initial variable. So let's say first we want to have a byte, so this is then byte 2 is equals 8, has 8 again. Then we want to access one of the nibbles, nibble 5, it's only 4-bit. So up to here we could also do just with, you know, a char array, but here we really see that we even can access individual bits, in the case here the individual nibbles. Then let's access one more, wait, 5, so the one next is 6 and 7, and then let's go with bits, 29, 1, comma, and the remaining bits are 29, 30, wait, yeah, 31, 32. Okay, so let's make a variable. Let's check whether its size is fine. Const int. Oops, size. Size of this thingy. It should be 4. Oops, that was the wrong comma. Suck, and it is. So we see we are very memory conservative. We are using just 4 bytes, and now let's assign some value to it. So we can use our flux variable name to assign some value. Some value we might like. Let's go with let's go with something like this. Okay, and now we can just run it, and we'll see that in the locals view already. We can access the individual bits as you see here. The last 4 are all zeros apparently. The nibble is 1. This nibble is f. Okay, let's maybe not go with 0, but with something that sets some of them. Let's go with 3. Now we should have the bytes further down set. Suck. You see now we have 2 of the bytes set, which corresponds in if you put it together to the value 3. And this way you could have really a whole bit field with individual bits having different meanings, enabling different functionality, whatever you want. And at the level of the programming language itself, it is super easy to access, because you then just write bit 30, let's say, is equals 1 or true, whatever you prefer. It's nomenclature. You can then test if bit 30 is 1, or you can just check if it's true, because it can only be 0, 1 anyways. Then do something else, and this way you don't need to mess around with individual logical operators to get the different values. But what you simply do instead is you can make the compiler do it for you. So if we put a breakpoint here and take a look into the generated code, then we will see that well, it actually doesn't need so many even operations. So what it does in this case here is it loads the value BTS bit set 1 DH. Where does it set 1 DH? That is unexpected. Okay, so it loads it into register, then it uses this operation. But why is this not just 1 DH? Yes. Okay, so the opcode, I don't remember all the opcodes by heart. There are like thousands of opcodes. I think the BTS is just, it stands for bit set, so it means in this register it will set the bit at the position specified in the argument. So if we would set it to 0 in the next line, then it would probably use BTC, like bit clear or something like that, also with the 1DH argument, or reset in this case, BTR reset. So as you see, it is quite it saves you a lot of typing if you do it this way, because those operations, if you would want to perform them by hand, would look something like this. So bit f flux, okay, set is easy, or equals 1, and we shift it by well, since we went here with numbering them starting at 0, that will not be quite correct, so we shift this by, I think we need to shift it by 29, because if we shift it by 0, it is the first one. Yeah, I think this is right. We can check whether it's the right shift here, because now it's again 0, so we can check whether here it will become 1, and now we want to set it back to 0, so we make the AND operator 1 shift, and then the whole thing inverted. So it's already, as you see, quite a few more typing. You need to think about the exact position in your bit flag, so it's not the nicest thing. Let's quickly run it. Whether the compiler is smart enough to... Well, the compiler implemented it differently. Move X O1. Wait, oh shit, sorry. Small typo. Bit shift, of course, needs 2 operators. Yeah, now it's fine. You see that the compiler actually implemented the exact same way, so it generated verbatim exactly the same code. We also see here that since it used the right offset, the same offset value, we really picked the right shift argument, but we needed to just write much more code, which is error prone, because we need to think, okay, so the 30th bit, that's really offset 29, since the bits are numbered from 0. So this approach is much less error prone, and it really is recommended over trying to manipulate bits by hand. But since manipulating bits by hand is a good exercise, we will schedule some homework. It should be easy enough. Homework from the 30/03/2023. Okay, so we already have our structure, but let's put this into a scope. And since I'm too lazy to type everything down again, we go with just copy. As I called it slightly different in this time. So the idea is to replicate all those operations here using nothing else but bit operations. So set So as with this example here, such operation gets replaced or re-edited to something like this. Such operation gets replaced with something like this, and just for completeness, int test is equals which let's go with the 32th bit. So here this would be then replaced with punct flux. No, that's too easy. Let's go with the not so easy example. Okay, 32. That gets shifted by 30 in this direction, and then the whole result needs to be end with 01. Suck. Okay. Yes, so all those different things as you see here need to be changed such that you only use operations as in the above example. Any questions? No questions? Okay. Yeah, since this is kind of straightforward, I don't really have an idea for an optional assignment for this particular part of the homework, so there will be nothing optional in this homework here, unfortunately. But I think it is quite an easy homework, so it should be easy to do. And since you can use the locals output and also you can just print values to the console for debugging if you want, it is quite easy to check whether the result of your operations always matches the result of the... I have an idea, original code. I have an idea for an optional assignment. Using the so the idea here is really that you save your that you can first validate always the, like you would have two flag values. You would have flag value and then some flag value test, or rather you would just leave the flag var fu as is, and you would have you would create a mine. This we don't need. You would here assign the same value, and okay, it's not here, it's not quite right, so this will leave here as this is our reference value we want to work with. Let's just switch this to 3 and start from here. So then you would rename all the variables, like have your own char test, char my test 1, and so on and so on, and for every operation you would then, after you have your own version, have different variables which have a slightly altered name. And of course, and at the end, or if you are just doing line by line, then you can have an if that compares your value with the value that the original example has generated. And if they are the same, then you say fine. If they are not the same, then you report an error. So if you want to see how that would look like, especially, so we would go with my test here. Oops, my test, and now you can use the control flow structure. If my test is equals test, then f. Okay, so printf is a function, we have not talked about it, but it allows you to print text to the console. You can also add parameters, but we don't care for this now. We just use it to print a single string. You can also use cout if you prefer that. Fail, and you maybe should write test. My test is okay. My test failed, something like this. And then you can of course repeat that. For the uppercase, where you do the same thing, my f okay, so for your test you should of course use your own flag, and for these operations what you would do is you would oops, make the operations on your own thing, and then here after the operation you would say if var_u is punct flags is equals var_u f punct flags. As you see, you don't need to check all the flags at once. Since we have a union, we can super easily check all the values at once. Okay. Etc. And then you of course would repeat this for the other case here as well. And this way you can write a program that will validate itself and tell you whether you did the homework right or not. So that's the optional assignment. If you are convinced you did it right, then you don't need it. If you are not sure whether you did it right, you can do the optional thing, which will first of all ensure that you will do it right, because otherwise it will print fail. Plus it will give you some bonus points. Any questions? If not, we would proceed to function calls now. Okay, no questions. Then let's save this. As usually, I will upload this to the Moodle later today with quite a few more comments added. I think it's reasonable to not write comments during the lecture, because I get my fingers entangled too much if I try to talk and write at the same time. So it's easier for me to just write down the comments when I don't need to speak at the same time. And we unfortunately don't have like a speech recognition in Visual Studio that I could just dictate the comments. That would be fine. That would be really nice. So we close this and we open and create a new project. We will call it functions. And if I remember my plans correctly, that will be the last part, which will require a deeper dive into the assembly part of how everything works, so to say, under the hood. Since I think no, not quite. Maybe the more we progress with the lecture, the more high level it will become. So we'll still take a look into probably some smaller assembler thingies, but we will more and more just stay at the level of the C language as such. So if the assembler at the beginning didn't scare you away, that's already a large achievement. Zack. So as if you know any programming language already, you know function calls, and you might have been wondering how those work under the hood. How does the compiler how does generally a processor executes function calls? Because function calls seem to be quite non-trivial. You can have, of course, a return value and arguments, but also you can have recursion. You can have functions calling functions calling functions. You can have a function call itself, etc., etc. So it's a highly flexible thing. And one thing important to know is that in C, and so that on a hardware level, let's start from this, function calls are only very loosely defined. So the way they are in the end implemented is of course guided by which tools and mechanisms the hardware, the CPU offers you, but it also gives you a lot of liberties. When I say you, I mean in this case the compiler and language architects, not the average user of said compilers. But it's important to know that a function calls may look the same, but in fact behave differently under the hood, at least on the 32-bit architecture of in Windows. For a 64-bit function, for the 64-bit code, in fact, all the different function call conventions have been all simplified down to pretty much just one for integers and one alternative when used with floating point numbers and other special registers. So the things got greatly simplified, but if you are using something older that uses 32-bit code, then you need to take care of choosing the right function calling convention. Normally there are some default assumptions about calling conventions which the compiler will by default choose for you. You can change the global calling convention somewhere under code generation. Where was that? All options. Here, calling convention. So as you see, there are quite a few available, and they are not, this is not all they are, just the ones that you can use under Windows. Like for example, Linux will have different calling conventions internally. And again, if you switch from x86 to ARM platform, then the calling conventions change again. Although they have a lot of similarities with the ones at used by the 64-bit version of x86 architecture. They're just updated to reflect the fact that on ARM you have much more registers available than on x86. Okay, so but before we take a look, a deep dive into the calling conventions, let's just start with something very simple. Let's create our first function, or rather our first self-written function, since by creating the project the compiler already created a main function for us, which is the entry point where our program on C and C++ starts. Technically the name main is just defined as a convention. The entry point could have pretty much any name, and you could somewhere in the options change your entry point as well. Maybe nothing on the linker. That was linker. All options. Entry point. Yeah, it's empty, but it then just assumes based on other presets which entry point to which function to use. And for example, on Windows it would be underscore vmain, etc. In other projects, but for now we will just leave it empty. We can later maybe for funsies switch from main to something else. Oops. As you see, when it loses focus it switches away, but normally in most programs you just start with main. And but let's, as I said, write our own first function. So the notation to write a function which is not part of a class is just you write the return value, which is int in our case. Then you write the function name, and then in brackets you specify the arguments which can be passed to the function. Let's say int my arg1, comma int arg2, arg2, and then you use curly brackets to specify a scope, so the function body. And here let's go with the simplest things of them all. Int red is equals arg1 plus arg2, and then we return the value. We could of course simplify this, just write it like this, but let's keep it this way so it looks nice. And you might at this point wonder, okay, what is it if I want to make a function which does not return anything, which just does something and keeps the result to itself? First of all, you can just make a function that just always returns true or returns 1, but you can in fact also write it like this. You can use the void keyword. Void means that it's like a placeholder for a type, but it says there is no type. So void as such is nothing, and void while when using pointers, you have seen me probably using void asterisk already in the structures example with the different API options. Void asterisk would be a pointer on something, so it's a pointer without saying what it points to. It's just a memory address without any further type information. And for function, if you have the return type void, then the function will just do something inside and don't return anything. Okay. And now let's quickly call our function. So as you already also have seen me use it, maybe first we need some variables. Int var1 is equals 1, 2, 3, and var2 is equals 4, 5, 6. Okay, so you've seen me using functions already with, for example, printf. So you can probably deduce how a function call works. You just write the function name, then you write the two variables. You can also write an literal directly. You don't need to use a variable. You can also write a I don't know, equation. You could also have another function as an argument assuming of course that the function returns a value. You cannot use void functions in in equations, obviously. Yes, and we want of course to save the return value, so int ret is equals my function. So that would be the simplest case if we remove our additional 2 argument here. So let's put a breakpoint here and let's see how the function, how the compiler has implemented this internally. So yeah, so we are on the 64-bit platform, so things are a bit simpler. Although we see here again this just my code feature, we should quickly disable the things we don't want, which usually just pollute our nice clean assembly. Where was it? The general, just like this we don't want. Code generation, basic runtime checks we don't want. We don't want any here. That should clean up the code already quite significantly. Yes, so you don't see all the details, unfortunately, because it does some of the things here at the top. So when the main function starts, it will save the RBP register to the stack, and then it will allocate 70, well, hex 70 is, I don't know, nor x70 is, damn it, we don't want hex display, 112 bytes on the stack of new memory. As I mentioned already, the stack is by definition growing downwards, so to reserve some memory on it, you just subtract from the pointer instead of adding. And it reserved quite a substantial portion of memory, quite a bit more than what would directly be needed. And then here it places those 2 variables in memory, so it copies to the top of the reserved stack region. Wait, it does one more thing here. It to the RBP register, it writes the position of stack pointer +20, so +20 is something like 64, I guess. 32, okay. Yeah. So in RBP we have another position, and then starting from this position it can it has located its variable. So the one here is directly at RBP, and if we turn this off, then we see that the next one is just 4 bytes further down. Or further up rather, since we add plus. And then here we have the function call. So as you see, it will now copy the variables into registers EDX and ECX, and then it uses the call opcode to call the function. And what you don't see here is that the calling convention for x86 specifies that there must be a reserved area on the stack large enough to hold 4 64-bit variables. So this is the 32 that you see here, and this area will be available to the function internally already as a scratch area. So a very simple function will not need to allocate its own stack space. It can use this scratch area to do its operations. Unfortunately, the way the call here was created kind of abstracted this away, so we don't see this explicitly being done, but you see this, for example, implicitly here by the fact that where the RSP pointer points to. So if we go RSP, so RSP is this much, and RBP will be slightly more. So if we subtract them from each other, we get the 32. So you can, the idea is you can use RBP in plus. I should maybe draw that somehow. So I'll just draw in Paint because that's probably much faster than drawing than trying to write down all this as a comment. So we have some stack space used by the previous function call, which just grows downwards as set stack. Oops, that's the wrong one. Stack space grows downwards, and then when we enter the function, then we will allocate some memory again for our own variables. And then we will allocate some additional memory for the next function. Well, technically the drawing, maybe let's do it like this. We allocate a larger portion on the stack here. Let's write it like this, and then within this we allocate something for most of this is for our variables, and a small portion of that will be allocated for the next function we call in case we need it, in case it needs it. And then within this green region, so the addresses go up, the stack grows down. So if here the color, let's go with green, RBP points here, that's too big. RBP points here, and the stack pointer will be pointing at the end, of course, at the next empty position in the stack. So it's there. Another thing to keep in mind is that that the use of the RBP, so the base return, so the R just is a prefix used if you have 64-bit. On 32-bit it would it would be EBP. On 16-bit it would be just PP. 16-bit code is pretty much unused nowadays at all, so it's not relevant. But as I said, an important thing to know is that the use of this BP register is optional. So you can more or less achieve all the same things just by using the RSP and add to it different offsets. The nice thing about RBP is that if you would write assembler code by hand, it would help you easier to keep track where what lives in memory if you use the RBP pointer. And the compiler, when creating a debug build, will use this RBP pointer as well, because it generates better debug information. So by saving and restoring by saving this pointer to the stack and restoring it from it all the time, you can then walk back the stack very easily to the function before and the function before and so on. If the compiler, however, is set to generate optimized release build code, it will often opt for not using the RBP pointer for its intended purpose, but instead just use it as one additional general purpose register. So this is something to keep in mind when thinking about writing code in assembler or when debugging, that it will change the register use between the debug and the release build slightly. So as said, maybe here we can also write down that the two variables will live. So they had the pointer points here, and then we go. No, sorry. Where did the RBP point at? Push RBP, subtract. Yeah. Okay. Yes. So, oops. If we want to add a few minor informations just for the completeness here, let's make the text slightly smaller. Here leave our two variables var1 and var, I think that the order was different. It was var2. var1 was lower and var2 was +1. Was it like this? RBP was var1 and var2 was RBP +4. Yes. Yes, so this is how this is laid out in memory, and apparently there is quite some additional unused space since we have reserved 128 bits, of which we only need, well, 32 of course for the function call, and then 8 for the two variables. So for whatever reason the compiler here was quite wasteful with its memory use. Usually when you have larger functions, this will be better. But anyhow, having said that, let's now step through the code, and once we are here at the call, we should take a look onto the registers, and what also will be interesting is memory at the position of RSP. I will move the memory to the damn it, that was not the right what I wanted to, I need to drag the registers. Do we see it? All of them? Yeah. RSP. So if you drag like here, then you drag the whole panel. You need to drag the tab if you want to just extract one of the tabs. So now if we make the call, so we make a step. Did this move us? It should have marked jump. It should have marked in. That failed for some reason. Wait a second. Also, one more thing. You saw it didn't bring us the function directly when we wanted linker. Incremental linking. No. We want the code to be as simple as possible. Okay, let's see if it works this time. So we make step. Shit. As I mentioned already multiple times, if you have the focus on the code and not on the assembly, the single step steps by whole lines. Okay, again, memory RSP. Sorry, hex display, and okay, it points to something, and it is okay, let's go with okay. So now when we make the call, you will see that the instruction pointer changed and the stack pointer changed. Yeah, and here it worked. And here you see that a value pointed at where the stack pointed. So initially we had at the RSP, the old one, at this address just contained FFF. Now of course the RSP has changed, but we can then now inspect the old address. Why is it still FFF? We have seen that it changed. Damn it! It should have been. Okay, let's redo the example once more. Okay, we are here. We go to the call. RSP. RSP shows us B0. Where is this? That will be somewhere here. I can just okay, so I just wrote garbage to the memory, but now we see where the RSP is pointing, as we should have used RSP -1. Okay. I think that's the right address. And now we make the step. So the RSP changed, the memory here was altered. And if we now try to read this memory area, we should get an address. And the address here we got is the address in our main function to which the execution shall return once this function terminates. So what call effectively does is it saves the next opcode to be executed, the address of the next opcode to be executed, to the stack, to the memory at the location where the RSP pointer points to, and then it advances the RSP pointer by 1. So going back to our small drawing, after the call we got here one single entry. Okay, that's a shitty color. Let's go with something that is better to see. Suck, which is the address to return to. And this call and later return mechanism is at the core of how all the function calls on the x86 platform operate. On ARM that works slightly differently. If you are interested in it, and if we have enough time today, we can take a look on that. But well, we will see how quickly we advance with the material. It's good to know one of the mechanisms. You don't need to know each of them, how each of them differently works. So for now we will skip the internal part of the function because we don't really care about that. We just are interested in this return instruction here, so we continue, just skip the mathematical operations which we have already looked on with variables long time ago. And here you see that what happens is, first of all, we use a move operation to move the result into the ARX register. If you would return a 64-bit value, then it would be the RAX register. And this is the way how by convention return values are returned in simple cases. So when the function terminates, it will leave in the ARX or RAX register the value it wants to return to the caller. In special cases, i.e. like when using floating point numbers or structures or similarly other non-trivial objects, then this then the way the return works will be different. We'll take a look on it later on. But for the simplest case, just normal machine types, normal integer machine types, it always uses the ARX register, so it saves the return value, and then the function as such needs to return. So here we see that it restores the original value of the of the stack pointer, which it saved before at some point. RBP here, move, no, where did it save it? No, push RBP. Yeah, it just saved it by push now, but then it pops RSP, then it increased RSP. It should have saved RSP somewhere. I will need to take a look on that in a second in more detail. But as said, it restores the value of the RSP value from the stack. I think effectively it will just load the same value. We can check later whether RSP and RBP have the same value once we are done with layer and pop, because I think that what it does here is it will load the same value as it's saved here with the push. That is the only thing that would make sense, since we are missing an explicit write to memory. But since those registers sometimes mirror each other, that would be reasonable. The thing about the push and pop instruction is that they so the push and the pop instruction, I didn't explain this as yet either, since we haven't seen it before when just playing with operations. So we have the push instruction, for example, here. What it does is it takes the value of the RBP register, or of whatever register you actually specify to it. It saves the value to the address the RSP register points to, and then it advances the stack pointer, so the RSP register, to the next free slot. And the pop just does the opposite. It takes the value, so it subtracts one position from the RSP register, one position being 8-byte in our case, since we are on a 64-bit platform right now. It takes the value pointed to which this register points in memory and writes it to the register specified. And layer is just load address, which just takes a value from a specified location and then adds to it. So here, let's do the two operations. So it loaded those two registers with the previous values that the calling function expect to be. So the convention, the calling convention, for example, says that the RBP register should not be altered by the function, by a called function. So if you have a value in it and the function would want to alter it, it can, but then it must restore the original value before returning to the caller. So this happens here. It restores the original value using the pop operation, and now since it also restored the address, the value of the RSP register to what was when it entered the function, the RSP register should be pointing to the return address. And now the ret instruction will do two things. It will take the value pointed to, so this return address here, set the instruction pointer to this address, and again subtract one position from the RSP register. So you see here the RSP was changed by 8 bytes, and the instruction pointer now points to this operation, which is now after our call, which will just take the value, the return value of the function, which is in the rex register, and write it to memory on the main function stack. So this is the simplest case of a function call when we step through it one at a time. And I think this might be quite a lot of things to grasp at once. So let's contemplate about it, and I'll ask you, do you have any questions at this point before we proceed to other calling conventions and alike? No questions? Everything clear? Okay. Well, since we are supposed to make at least some small breaks during the lecture, let's make a 5 or 4 minute break and continue at 16:50 sharp. And if you come up with any questions in the meantime, I'm here ready to answer them. Okay, so I see there were no questions. It's time to continue. So for now we just taken a look on the simplest case where we are passing simple machine types, but an interesting use case will of course be the passing of structures. And since we had structures today already, this is particularly interesting. So let's create a simple test structure, which let's just copy and paste since we don't want to waste too much time in typing, and use a test function that uses this structure. Here we can just copy our previous function and add one argument, mystruct arg3, and let's use it for something. So let's say arg3.value1 is equals arg1 is equals arg2, and then let's say this is equal 2, and var3 something like this. Okay, now we will also need to initialize our test structure with a few values. Let's say we just initialize everything to 0 and we make a function call to our new function. So right, var2 and var3. Okay, so the way this is written here, we will be passing a copy of the whole structure to the new function, so that these operations here internally will not really have an effect. It will of course alter the copy of the structure, but it will not propagate out to our calling function. So let's take a look how this looks in assembly again. So you see here this behavior we already saw once before. It uses the repsmooth opcode combination to copy a memory block, in this case our vars2, into a new memory block on its stack, and then it will be passing values here to the function. And you see here the use of the R8 register, which together with the EDX and ECX are used to pass values to the function. For now we have only seen 3 of them in use. There are, with the normal standard 64-bit calling convention, up to 4 registers which can be used. R9 is the 4th one, and if we take a look on a function that has more arguments than 4, we will see that the remaining arguments will be just passed on the stack, which we'll take a look into shortly. But for now we see that effectively what is passed to the function is the values of those 2 variables and the memory address of a copy of our myvar variable. So if we now enter the function, we see here that it just does the operations. It accesses the memory at the location pointed by the pointer. So it internally, maybe let's start from the. So first, the thing that in this case the function does is it saves those 3 registers onto the stack space which was given to it by the calling function. As I already mentioned, there is this space reserved for the function here, and it now uses this space to save those registers such that it can reuse them. Once it's done saving, then here it on its own stack space which it extra allocates, saves the stack pointer, sorry, the base pointer. Then it reserves additional space on the stack pointer, copies the new stack pointer to the now available base pointer register, and then it does its operations, and at the end it undoes everything it did to the stack and then returns. So this at this point of course is yet already quite useful, because it allows you to pass a whole structure at once, but it this operation requires a lot of copying around. So this is maybe not something that one would necessarily want. Or perhaps yeah. Plus, it doesn't allow you to get the value out which you have, which were changed in this struct. If we want that, let's try another case. Let's call the function sr for reference, and then pass here the reference operator. This will pass now the argument as reference. So instead of creating a copy and passing the copy to our function, it will just directly, sorry, we don't need to write this, it will just directly pass the memory address of the structure as it lives in the stack of the calling function. So you see here it is much simpler, just writes the address of my vars into R8, the two other variables, and then it calls the function. The function internally will look almost the same. Well, actually it will look exactly the same. We can take a look into it quickly. Zack. As you see, nothing really changed. It saves those registers, it creates some stack space, it makes its operations, and it returns. So the function effectively is the same, but this reference operator here in its prototype tells the compiler that when the function is invoked, it should actually pass the real pointer to the structure and not to a copy. So as said, the upsides of this are no copy operations, so you are already saving some CPU time. The downside is of course that then here you can alter your structure. What you could of course do is you could write const, and this is in fact used quite often. So if you are passing structures or other things which would be alterable by reference and you don't want to alter them, you just specify const. Technically you could of course within this function use typecasting to override the const, but that's not something you are supposed to do, and unless you do it on purpose, you will not accidentally assign some values where you shouldn't. But here you want that. So the nice thing about using this without const is that this way you can make a function return multiple return values, although slightly indirectly. You can of course use this reference operator also with a normal variable, so we could also just have a bunch of variables to which we are returning individual return values. But of course there is another method which is also quite similar, namely to pass it not by reference but as a pointer. The difference by writing the code is of course that you need to use the arrow operator, and when you be invoking the function p, then you will need to use the reference operator here instead, p. See, now it's complained, so we need to add the reference operator, and now if we take a look on it, it will again, so on the lower side it will look quite identically the previous call. Actually we can compare it here. It's pretty much exactly the same, no differences there. When we go into the function, we also see that internally also nothing changed. So this pointer or reference notation is, as already mentioned when we haven't taken a look on the normal pointers, quite interchangeable. The only practical limitation is that you cannot have a reference that references nothing, while with pointers you could in fact pass, for example, null here as an argument. So if you would want to be safe against such operation, we could have here just an if that checks whether arg3 actually exists, and if it exists then it uses it, and if it doesn't exist then it doesn't. And here we could use a dingstar trinary operator to either use it or not. So let's copy this, undo the changes here, and call it spsave. Safe in the sense that you can pass null to it and it will not do something nonsensical but actually properly handle the situation. The upper version here, as said, is unsafe because you could pass null and then it would crash basically. And of course, if you want to not have to check with ifs or alike here whether the variable was passed or not, you can just go for using this by reference notation, which necessitates you to provide a value, but then it also implicitly lets you know that you can address this value and that the function will work properly and will not crash. And analogously, as you can use structures as arguments in functions, you can also use a structure as a return value of a function. Of course, then a few things will change, as we'll see in a second. How do we call it, this one? I don't know, something. Let's call it RS for return structure. We will give it the same two standard parameters. Let's copy this body, just not that part, and then let's of course call this red. Here let's go with red 3 var red, and we of course need to define red and we initialize it with zeros just to be on the safe side. Okay, and now let's use it. My struct red s, my function rs. Now we can take a look how this will work, or maybe we should not mix too many things together. Oops, do it this way. So we have our structure keeping something, and then we assign something new to it. So let's take a look on how this looks. And here, as you see, we are moving var to let's see, cx. Okay, so in the R8 register as dword we write value. In the dx register we write the RBP, and in the RCX register. So if you remember before, we used CX for the var1 and dx for var2. Here the things shifted kind of by 1. On RCX, what it got here will effectively be the address of our structure, and the first argument now lives in the once larger register edx var1, and the R8 register, which before we haven't used in the 2 argument function, is now used for the second argument. So everything like shifted by 1, since we needed to pass to the function the address where it shall write the return value. And then we have here our call. So now let's go into the function. Zack, zack. Within the function the things are quite similar. We save the registers, we do our operations. We still copy to rex the address of red. So in this case we return the address which we before have gotten in by R8. We can we don't need to demonstrate that. Then we restore the stack and then we return. So we can use the jump out command to just jump out without stepping through the whole thing. Here we load an address in an address of the original variable we want to override. So internally here it created a new variable for the return value located at RBP plus 89 hex, and now that it has the return value, it uses this repsmove scheme to move to copy the bytes into our actual return variable. So it is quite wasteful. It probably would be more elegant if it would just pass the original address instead, as we did here, just at the beginning instead of the end. But I guess they decided to do it this way because once the function returns, this only the action of the function returning should change the value it is supposed to assign to. And if the function would, for example, throw an exception somewhere in the middle of writing to the structure it is supposed to change, then you would have an inconsistent state, because the function would then terminate prematurely. That might be caught by a exception handling statement, which is something on which we'll take a look later. And then the state of our mice struct would be something indeterminate. So to avoid such scenarios, even though it is more computationally complex, it will always return to a new memory region and then copy, once the return was successful, to the origin memory region where it wants the values to have. Okay, using pointers we have already taken a look at. So now let's take a look how this function call, or a function call, would look if we would have much more arguments. So for that, let's create a function which just takes 10 arguments and doesn't do anything in particular. And then let's call that function with 10 arguments. Zack. And let's see how this looks. So as said, here we are just using the simplest arguments we can. We just write static values to it, and here now you see the function call in action. We are using the aforementioned registers for the first 4 values, and then the RSP register, so the stack is used to keep the additional values for the subsequent arguments. This way we can pass an arbitrary amount of arguments to a function, but if we only have 1 to 4, then we can be particularly effective about it and just pass them through a register, which is faster than if we would always put them on the stack and remove them. Okay, so let's put a breakpoint here and take a look inside. One thing to note is that in principle the copy operation we saved before here are now still executed by the function here in its function prolog, but this is optional. So the function can copy all the data to the stack if it wants to, but it does not have to. The reason this was implemented this way is because there is such a thing like a variable argument function, which we'll take a look next. This is a function which can take an arbitrary amount of arguments, basically. So in order to easily be able to address all the arguments, it was necessary to do the call such that we can generate basically an array of arguments. So now if we have this, if we put a breakpoint here, and then go with and we see that the RSP plus 8 was used and RSP 0 wasn't, because RSP 0 now after the call opcode was executed will contain the address of where to return to. So if we in the example here go to our immediate window and we say that RSP will be a type in64. Is it correct? In64 should be. Let's see the increment used. The increment is for 8. Yeah, that should be fine. RSP is in 64, and we treat it as an array, so it's sorry, RSP plus 8. We need to make it plus 8, and we want the value. Then we get well, 1 was, I think, is the first value we passed. Yeah, we passed starting 1. Then we can 2, 3, 4, 5, 6, 7. You also may notice that the lower portions of the memory, the higher portion of the memory range here contains garbage, which is simply because we defined our function as using integers as arguments. So the opcodes here, the move opcodes use dword, not qword, and they only move 4 bytes into the memory instead of all 8 that would be available in the register. So then the higher portions just remained filled with garbage. But this way we internally have an array of arguments which can be really went through index by index by index despite the fact that some of the arguments are passed by registers. Okay, now let's take a look on this, on the next thing, the variable argument function. So the idea of variable argument functions is that sometimes you might not know how many arguments you want to pass to your function. In this simplest of all cases, or at least in this very simple case, what we do is we just want to calculate. We want to find the largest value out of a number of values passed. So we have a function and we can pass to it an arbitrary amount of variables, and it should return us the value of the largest value which was within these variables. So the way the function here now is implemented is that the first argument tells it how many arguments to expect. You can use this va start command to initialize the array with the arguments, but you need to tell it which argument is the last one that is specified, so it needs to know that. And then internally you can then use this va arg function to iterate by pointer through all of the arguments one by one. Yeah. And once you're done, you can of course call this, but when you actually take a look to the definitions, like this definition is pretty useless. It just sets it to 0, so it doesn't really do anything. It's recommended to use it, but you don't really need it. And while the other ones here are doing more. So this one actually initializes the AP variable to the first pointer, to point to the first element in our variable part of the argument list, and the next va arg will always take 1 and then advance the pointer further by 1, and so on and so on. And as you see here, it also wants to know which type to cast to, such that to get the right value out. So let's use the value now. We can feed to it again the same 10 values. Zack. Of course the result is pretty predictable, but not quite. We need to tell it that it will get 10 values. So now if you put a breakpoint here, we'll see again how it works. Just wrote 10 to the first register and shifted everything. And then of course within our function it saves the registers to the right position and then does its calculations. What it does internally is not so relevant, since it's pretty self-explanatory what happens here anyways. It just takes the next argument on each iteration and checks if the next argument is bigger than the saved max value, then go to the next argument and the next and the next, and so on and so on and so on until it's done. Yes. So these are variable argument functions. One example of a variable argument functions you have already encountered is the printf function. We'll take a closer look into it later, but as I mentioned, you can provide it with arguments. For example, in printf you can write some text, then you can use a something operator. So this something can be there are different letters which have different meanings. D will be for an integer. You could also use I. U would be for an unsigned integer. C for just a character, S for a C string, etc. But what then happens basically is that the function, while passes the string, if it finds a D, then it expects at this position to have an integer as an argument. So if we look to printf, you see that it is also with these 3 dots defined like a typical variable argument function. So this is like a more practical use case when you would really need to use something that really has variable arguments. With our previous use case, this one, you could also just pass it a pointer to an array you make yourself. You wouldn't need to use arguments. But I think on this printf function, it is pretty clear that you might use it in so many different scenarios, since you're using it to just output text, that you would really benefit from being able to specify some very complicated format. And then we would expect here a string and then another integer. Yes. So yeah, this is one of the use cases where you have variable argument functions. They are used in many places from time to time. They are not super common, and this is, for example, something which not every programming language has. So some programming languages don't support variable argument functions at all. Technically, you could of course always say that let's just replace this part with an array and then just always pass an array to it. It would be also doable, but would not be that elegant. So it's nice. It's a nice to have functionality of the language. Now, one thing we might also maybe want to take a look at is how this would look in a different calling convention. So especially just this use case where we just have different we just have many arguments and we want to see how they work. I switched here to 32-bit from 64, and this comes with a completely different default calling convention. So as you see here, it pushes all the values onto the stack. It does not uses registers to pass arguments at all. And by default, the way this calling convention works is once we enter the function. Okay, so now we are here in the function. It does pretty much the same things as it does normally. Okay, I need to disable some useless functionality again so that we get a clear. We don't want this. We don't want this. General support. We don't want this. Optimization and we don't want runtime checks. Okay. Let's run it again. Okay, so of course the call didn't change much, but the function is now much more readable. It's much shorter. It just prepares a stack and then it clears the stack. But one thing you can notice here at some point is that it will remove from the stack all the things that were added to it. So when we go back to main, we see that we pushed a lot of things on the stack, we made the call, and then we just are saving the return value. Sorry, that's a different calling convention. Okay, so in this case, apparently the default calling convention is that here this add ESP 28 hex will undo all this, so it will subtract the amount of arguments that was added to the stack. So in this calling convention we had right now, the function really is just responsible for itself. And the caller is responsible for cleanup. Right, that's the other one. You can specify a calling convention with these keywords here if you prefix the function name with them. I think it was std call which requires. Yeah, okay, so what we had before by default is the standard, so the ccall like here. Now we will see that the function looks the same. The interesting thing is, as mentioned, for the 64-bit there won't be a difference. This is all 32-bit. Yeah, so this is now the default. Let's see, we can check here in the settings which was the default calling convention for our current configuration. Yeah, so that's the default one, and the Windows API uses the std call, this one, and this one is that's what I wanted to say before I noticed that I didn't have the right line enabled. Here you see the cleanup code is missing, so it pushes things to the stack, but it does not correct the stack pointer once the function returns. This is because the function as such here uses a ret instruction and tells the ret instruction how many additional entries to remove in addition to just the one return address from the stack. So this was in principle implemented to save on program size. So normally you have functions and the functions are called a couple of times. So if we assume that every function is called at least once, if you would have the cleanup code where the function is called, we would have much more often the cleanup code than if a function would be responsible for cleaning up after the call on its own. And hence the Windows standard calling convention was implemented such that the called function will do the cleanup on 32-bit systems, of course. This saves a couple bytes, and in the time where you had only a few dozens of megabytes, 100 megabytes was already a lot of RAM in your computer, then every byte counted. Nowadays, if we switch to 64-bit, you will see that those calling convention specifiers are pretty much meaningless. So as you see, it's always the same method with registers and no additional cleanup. So here we are not using push, but so we don't care about memory. What we care about nowadays is CPU speed, because memory, you can always put in more memory, but you cannot make a processor faster than what is currently available on the market. If you need a faster one, you need to wait and hope there will be an advantage. So the way nowadays it is done is that when the function is set up, it will allocate all the memory it might ever need to pass all the arguments, and then instead of push instructions, it just uses move operations to put the arguments on the stack, and then it does the call. So you are trading in memory use for computational speed, because then you won't need to clean up the stack afterwards if you have already all the stack pre-allocated from the get-go. But going back to the 32-bit case, there is this calling convention called fast call, which should look familiar to you. As you see here, it kind of calls in the same way as 64-bit, just that it only uses 2 registers instead of 4. It is used fast call because it's supposed to be faster than having to push things to the stack and then pop them out. Also in this calling convention, as you see, the called function as well is responsible for the cleanup. So yeah, that much to this. Any questions at this point? No questions? Okay, then maybe a last thing for today. Let's create a small other function which will take a different type of argument. So let's go with double. We need to give it a name, D. Let's go. And let's see how it looks when we are using a different data type, not an integer. It will use different registers now. So here, as you see, it uses the MMX registers instead. Other than that, the call is quite similar, so we can do the same thing for... Okay, we don't need to specify anything since we are in 64-bit back. D10. Yep. Okay. We won't care for the return value, and we'll just want to be quick about what we do, just for demonstration, to see how this looks here. And you see here, it uses the first MMX registers to pass the value, and the rest it puts on again on the stack. So it first takes a value, puts it into one of the registers, then it copies it onto the stack in the right position. It takes the next value, it copies it at the right position, and so on and so on and so on. And finally here it uses the same calling convention. So this is differently to 32-bit, where it would more often change calling conventions. On 64-bit, everything was simplified down. They need to use different registers, but other than that, it's similar. And if we would have, in fact, mixed integer and floating point numbers, then it would keep the numbering, the same numbering. It would just switch registers, so it would not use all the registers that it could use, but it would just use first 4 and then the stack as the data come. Okay, and maybe one very last thing about functions. As we have learned about pointers, we can also have function pointers. So let's define a function pointer, which is quite easy. Let's say we want to call our first function using a pointer. So the notation for function pointer is like this. So we have the return value, then this is what will be our variable name effectively, and then you have the argument list, although you don't need to specify the name since the names are meaningless at this point. And then we can just assign to our function pointer our function and then we can call it just as if it would be a normal function. So the compiler knows that this is a pointer, and then will implement the call for us. If we put a breakpoint here, you will see that it will behave slightly differently, well, mildly differently at least, because before, when we had a call, it like the call was hard coded. It just knew the relative address to jump to, while here it calls an address at a given memory location. So it reads the pointer and then it jumps to the pointer's address. And this is actually quite useful because you can implement a function and then give the function another function as an argument. So for example, if you would have a function that sorts a list, but you want to define the sort order. So let's say your list contains structures. So obviously for an integer it's simply to say what's larger, but for a structure you don't have larger or smaller operators defined. So you would then provide an own compare function, which would then tell the sorting function whether the two values, which of them is larger than the other. And this is just one use case. There are many other use cases where passing function pointers is very useful. Whenever you want to create a more complex execution flow, passing around pointers is a very helpful thing to make your functions behave differently, especially if you are writing just in C and not in C++. In C++, if you want to make things behave differently, you have a lot of other methods like inheritance, passing objects, which have some function defined on them. Internally, this again unwraps to a sort of function pointer, but is less explicit. But in normal C, where you are highly limited in what you can do, using function pointers is a very useful tool in your arsenal. So we already are at the end of the time, so we only have 1 minute. So are there any questions? Are there no questions? Okay, so if there are no questions, then we will stop at this point. There are a few more things about functions and stack which I wanted to show you, but apparently I was talking not fast enough, so we will take a look on that next time. But don't worry, these are more exotic aspects to how all this function call mechanism works. So it will not be something that you will be missing now during the holidays for your homework or anything of that sort. I think we'll see each other in 3 weeks from now, if I'm correct. You have, I think, 2 weeks of holidays. So have a happy Easter or just happy holidays, and we will see each other next time. Bye bye.